Okay, so what is a function? I really enjoy asking this question at interview because it really demonstrates the difference between university maths and school maths. So at school, you have some idea of what a function is, right? You kind of are used to an input, you get given an input, and then you pass this to a function, and then the function gives you back an output. Okay, but you aren't given anything towards a formal definition of what a function is. Okay, so maybe to be more concrete, not completely formal, but to be more concrete, we're gonna we're gonna describe a function as this. So a function is a map. We're gonna call it a map from a set called the domain. A set is just like a collection of numbers, a collection of objects, right? From a set called the domain to a set called the range. Called the range. So a good picture to have in mind is you have this as your domain, and you have a bunch of numbers in here. We'll just mark them as points. And you have another set of numbers called your range. And then what f does, the function f, is it maps points in your domain to points in your range, okay? We'll just match these up. Maybe this goes here. Okay, so this is a function. So nothing hits this guy. Two things hit this guy. Blue is applying f. And these, this gets mapped to this gets mapped to this. Okay, this is kind of the picture you want to have in your head of a function, right? So a question I asked in when I was doing interview prep is, can you give me a bounded function? Now, what do I mean by bounded? So again, you maybe have some idea of a function which is between two kind of lines. So if we have this, our graph, then this function here is kind of bounded in the sense that it's always between these two lines. Okay, and that's kind of what we mean by bounded. We mean that there's some values which it never exceeds, both in the positive and negative direction, right? So a good example of this, if you want to define over the real line, is, for example, the line like this, the line of y equals x between 0 and 1. Okay, so this is the line, or this is f of x equals x. Just label the x's. This is y, and this is x. And this is bounded by 2, because 2 is bigger than f of x, is bigger than minus 2 for any x. Note that here we're specifying our domain, so let's reuse. I'll just show these relate to each other. So the domain is this set. This is the closed interval from 0 to 1. Closed interval. So like a half, you could have like 1 over pi, any real number between 0 and 1, including 0 and 1. Okay, an open interval would have more curvy brackets. It would look like this. And that means excluding 0 and 1. This is an open interval. Okay, but by defining it over this restricted domain, remember we're allowed to do that because part of the definition of a function is the domain, then it's bounded. Okay, it's bounded by 2. Another example we could define over the whole real line is, for example, sine x. So sine x goes kind of like this, okay, and all the way to negative infinity, and this is of course bounded by, well, anything bigger than 1, so it's bounded like by 152 and minus 152. Okay, you don't have to get close. It's true that it's bounded by these two. You can get a smaller upper bound and lower bound, but for now we're just interested in bounded. So sure, it's bounded by 152, and that satisfies our definition of bounded. Okay, and then I asked for a function which isn't differentiable everywhere. So now we want a function which isn't differentiable. I'll explain what that means in a minute. Differentiable everywhere. Okay, so differentiable means the derivative exists. So for example, in this graph of say y equals x squared, not bad, y equals x squared, this is y, this is x. This is differentiable everywhere because the derivative dy by dx is 2x, and this can be evaluated at all values in the domain. Let's say the domain is R. The domain is R, this is the real line, all real numbers. And sure, you can throw in 0, you can throw in 100, you can throw in whatever you like here. So we want a function which isn't differentiable everywhere. So there has to be a value in the domain for which the function exists, but the derivative doesn't always exist. And a good example of this is a modulus function. Okay, so if you have f of x equals mod x, what does that look like? Well, for positive x, it just looks like y equals x, and then for negative x, it looks like y equals minus x. And the point is, this is a point there. You can't say what the derivative is here. I mean, you can look at the definition of the derivative and see it's impossible to say that. But intuitively as well, I think this is a corner, and you can't have a gradient, which is kind of what we mean by the derivative, at the corner. Okay, so this is an example of a function which isn't differentiable everywhere. The difference again with this is that this is smooth, and so it makes sense that we can draw a tangent line at any given point and come up with an approximation to the gradient, or in fact the exact gradient at that point. And finally I asked for, so finally we want f both, we want f, I'll rewrite that. We want f both not differentiable everywhere and bounded. So this is like not differentiable everywhere and bounded. Okay, then we can just restrict this to some finite domain. Okay, so some finite domain, some closed interval. So for example, for example, let's combine both our ideas so far. This is -1, this is 1, this is 1, so this is a function f of x equals mod x with domain -1 less than or equal to x is less than or equal to 1. Okay, and the point I made in the interview that I did was, actually we don't need to limit ourselves to real line functions at all. So the reason that people always come up with functions like these is because that's all they've seen before. As far as their experience goes, functions are lines on graphs, okay, where graphs are like vertical axis and horizontal axis, okay. But a function, if we go back to the definition, well, the description, can mean so much more. It's just a map from a set called the domain to a set called the range. So a really simple example which solves all of these is, for example, um, if we define our domain to be the set 0, 1, okay, it has the numbers 0 and 1 in, and f of 0 is 0, f of 1 is 1. Well, this is bounded by 2, for instance, and it's not differentiable. I mean, what's the derivative at 0, right? It doesn't exist. And you can plot this if you want. It looks kind of like sorry, wrong color. Looks like this, right? It's 2 points here and here. And that's kind of a really simple way to solve this problem. And the reason we came up with that is because we didn't restrict ourselves to a conventional domain, okay? When you're defining a function, you can define your domain as whatever you like, okay? As long as your function is well defined over every value, i.e. whatever value in the domain you give me, my function can give you a value in the range, then it's fine, okay? And so it's really interesting to see how people approach this problem, because it really, as I said at the beginning, shows the difference between school maths, where you work from intuition, and university maths, where you work from definition. And you really, as I said to candidates who I interviewed, you really have, like, you can be God, you can play God in the realm of maths when you start to realize the amount of things you can influence and what you can write, and really understand the boundaries of different definitions and ideas.